uh, introduction of fundamental equations of heat conduction. Fundamental equations of heat conduction in previous class. Okay, this these equations are general insights, means this is general. I am going to derive the general heat transfer rate equations for conduction in Cartesian coordinates. I will be going to cover general heat transfer heat conduction equations. First one in Cartesian coordinates. Cartesian coordinates, and second I am going to derive general heat transfer conduction equation in cylindrical coordinate. Cylindrical coordinates, and number 3 spherical coordinates. Or I can say three-dimensional heat conduction equation, general three-dimensional. First one, if I say this one, general three-dimensional heat conduction equation, this you can call it as general three-dimensional conduction equation in Cartesian coordinates. You can say the once it is derived, you can call it as a general three-dimensional equation for cylindrical coordinates, and this you can call it as general three-dimensional equation in spherical coordinates. Okay, with limiting that conditions, we can derive, we can make these equations into one dimension, and we can apply these equations either to the steady or as well as unsteady flow conditions, and with and without heat generation. Okay, first I'll going to derive equation, generalized equation for three-dimensional Cartesian coordinates. Let me talk about that one, and then we will go to the cylindrical coordinate system afterwards. Okay, now first I will take a case of general case 1, I mean Cartesian coordinates. Cartesian coordinates. We know that Cartesian coordinates normally denoted x, y, and z directions. Okay, so for which I am taking a small elemental cube. For which I am taking a small elemental cube, which is placed in the space x, y, z. This is y. This is x. This is y, and this is z direction. Okay, in this direction I am taking a elemental in x direction, have a elemental thickness of dx. This is thickness of dx, and this has in y direction has a thickness of dy. Okay, and You just excuse me, the lines are not straight, but I'm trying to draw it with a stylus. It is very pressure sensitive stylus, so sometimes the lines are going to be thicker, sometimes the lines are going to be thinner. Okay, so this is other direction, it is in z direction, so this is going to be dz direction. This is calling as dz direction. This is dz direction, in z direction, dz. Okay, so now elemental volume first. I'll take the elemental volume is, I'm writing elemental volume. When what is the elemental volume I consider is elemental volume is here dx into dy into dz. Okay, now so in this elemental volume, now I'll try to derive equation for three-dimensional heat conduction equation. So for which I am, with the help of a first law of thermodynamics, with the help of first law of thermodynamics, with the help of first law of thermodynamics, first law of thermodynamics, I do the energy balance. The energy balance is the energy balance is net heat conducted into elemental. Now I'll write. This is, I am resuming the discussion. I am starting that whatever we have discussed earlier class. I am trying to write it here. This is equals to net heat conducted into element top dx dy dz per unit time plus internal heat generated per unit time is equals to, I'll write here, is equals to increase in internal energy per unit time plus work done by element per unit time. Okay, so this I call it as 1. I call it as, this is 2. I call this as 3. I call this as 4. Now since here I am taking a solid, since the conduction is taking place in the solids, therefore work done in the solids because of the temperature difference is going to be 0. Therefore 4, that 4 condition, that is 4, which I name it 4, is equals to 0. Therefore now energy balance is 1 plus, therefore energy balance is 1 plus 2 is equals to 3. Okay, now, so now what I will do, I will go to that next slide, and I will again redraw that sketch according to my convenience. Okay, according to explicit manner to understand about the concepts. Okay, now I will take again, once again I will draw the sketch in large size. Ignoring coordinates showing axis, ignoring coordinate axis showing. Now this is my elemental cube. Okay, now this is now I will take can you able to see this dot lines, dash lines? Okay, this is blue in color, you can check it, this color right now. And as I said, this is dx. Okay, and this is dy. And this is dz. Okay, just forgive me here. This is this is dy. Okay, right now here let, according to my energy balance, according to the energy balance, first net heat conducted into the element of dx, dy, dz, or otherwise heat gain into the in the element due to heat transfer. I can say, let I'll say this is this surface area, it is nothing but the surface area of this one is going to be dx and dz. Okay, and this is going to be, the surface area is going to be dy and dz. This is going to be dx and dy. Okay, now let's heat is transferred in this direction like this to this element, like this. I mean in the x direction heat is transferred. Let us take the rate of heat transfer is like this. This I am denoting as qx, since it is taking place in x direction, so this is qx, and it is leaving after dx, then it is denoted as the heat which is leaving, that is denoted as q x plus dx. Okay, now similarly in the y direction, the net heat into the circuit, into the element, net heat flow rate into the circuit in dy direction. This is dy direction. If I denote it, it is like this. Sorry. Yeah. Okay. So this is qx plus the dx. Okay. Now in y direction it is like this, flowing in y direction like this. Heat transfer into the element is qy, and heat conducted out of the element in dy direction is q y plus dy. Okay. Now, and in z direction, if I take the z direction, it is like this, qz this way. Qz is here. Now it is, if I take, this is the direction of entry, this is from here to here dz, therefore I can say this is the direction with which it is entering into this direction. I'll take here, this is qz, and it just comes out in this fashion. This is q z plus dz. Okay, so this is a description of the element and the heat transfer rates. It is entering and leaving the elemental volume of dx, dy, dz. Okay, now if I want to calculate heat flux, you know that heat flux is nothing but heat flux we define as heat transfer rate per unit area. Okay, I mean, suppose if it is qx, means that heat transfer in x direction, heat flux qx heat transfer rate in x direction is equals to heat flux. Normally it is denoted by qx into x direction. If I take in this x direction, here I can say qx into, this is d, this is, I can say what is this is going to be dz, and this is going to be dy. Area normal to this heat transfer is dy and dz, right, and dz. That means if qx already we have defined according to Fourier's law, this is equals to minus kx into dou t by dou x, temperature gradient in the direction of x, into dy dz. Okay, similarly heat transfer rate, I mean here I mean to say this is equals to heat flux is equals to heat transfer rate qx by a, I mean to say q by a. Therefore this is denoted as q. Now q into a is equals to q, small q into a is equals to capital Q, like this. Okay, now next if I want to calculate heat conducted or heat entered into the element in the direction of y, rate of heat conducted into the element in the direction of y is equals to, I can say this is isotropic material, the thermal conductivity Kx in x direction, Ky in y direction, and Kz direction are same, and it is equals to 0. Therefore, the equation 1 will become dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square generated per unit volume. Okay, now, and this is denoted as watt per cubic meter. Now, as per my requirement, what is my requirement? The requirement is internal heat generated per unit time. Means I want heat generated in a volume of dx, dy, dz. Therefore, the rate the heat generated rate in the elemental volume is equals to elemental volume is equals to q dot into volume. What is the volume? I have it again, dx, dy, dz. Then the unit is going to be watt only. Okay, the unit is going to be watt only. So this is equation number 2, and this is according to my notation which I followed earlier. This is number 2. Okay, so I'll go to that. I'll denote this number 2. Okay, now I'm going back to third one. What is the third one? It is mentioned as increase in internal energy per unit time. Okay, I mean increase in internal energy per unit time. Let rho is the density of the element and Cp is the specific heat of the element. Specific heat of the element. Then due to heat transfer of Qx, Qy and Qz, and again which is going out by Qx plus dx plus Qy plus dy and Qz plus dz. So there is some heat increase in the internal energy. There is an increase in the internal energy of the element. So that internal energy, increase in the internal energy, I am denoting as defining as because of the temperature gradient. So I will define as internal change in internal energy as, I'm going here, change in internal energy as, normally we know that change in energy defined as normally in general from the thermodynamics fundamentals change in internal energy is equals to mCV, sorry, this is not subscript, this is M specific heat Cp or I can use instead of Cp, I'll use here only C for convenience, C, and here also for the convenience I'll use C P delta T, or here dou T, right? Now rate of change in, now here, since heat transfer we talk about rate of change in terms of time, we'll talk about, therefore rate of change in internal energy is equals to mc dou T by dou T time. But m we can calculate from the density, that's density into volume. Density is unit is kg per cubic meter, mass by volume, therefore kg per cubic meter into dx dy dz. Okay, this is mass on specific heat C. Okay, and dou T by dou T. Okay, this is third. Now, according to my definition, energy balance is equals to, energy balance I mentioned as 1 plus 2 is equals to 1 plus 2 is equals to 3. So what one talks is, what one is this one, dou square T by dou x square dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square K dx dy dz plus number 2, heat gained, rate of heat gained in the elemental volume of dx dy dz is found as q dot dx dy dz is equals to, just now you can see it here, is equals to q dot dx dy dz, and this is equals to, the third term is rho into dx dy dz into specific heat C into dou T by dou T. In all the cases dx dy dz is common, so I can cancel this one, and I can bring this k here and here also, means I divide it the equation by k, means I'll divide it by k, this entire equation by k, here also I'll divide by k. Now what will happen, this equation becomes dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus q dot by k is equals to rho C by k dou T by dou T. This equation is called as, this equation is called as generalized generalized three-dimensional heat transfer equation of conduction. Of conduction in Cartesian coordinates. Cartesian coordinates. So with some assumptions, with simplifications, we can written as, suppose if this equation is in 3 dimensions. Suppose if I want to calculate this equation in one dimension, in one dimension, this equation has become dou square t by dou x square plus q dot by k is equal to rho c by k into dou t by dou t. Dou t by dou t. Okay, like that. Suppose you can write it in y direction, you can write it like this: dou square t by dou y square plus q dot by k is equal to rho c by k into dou t by dou x. Suppose in this equation, this can be simplified, the equations can be simplified for the special cases, like special cases. First case is when no heat generation. When no heat generation means here q dot by k is equal to 0. Therefore, the equation stands as simplified to be dou square t by dou x square plus dou square t by dou y square, dou square t by dou z square is equals to rho c by k into dou t by dou t. And here this rho c by k can be written as 1 by alpha, where alpha is called as thermal diffusivity. That is equal to k by rho c. It is nothing but how fast the heat is diffused through a material during a change of temperature with time. Okay, this where alpha is called as thermal diffusivity, that is defined as k by rho c. It is nothing but how fast the heat can be diffused into the material with a change of temperature in a given time. Okay, right? So now, so this equation, this first equation, special case, in the first case we called as this equation, this is called as, this equation we called as Fourier equation. I'll write it next place. This is called as Fourier equation. This first case, sorry, this is called as Fourier equation. Fourier equation. Okay, now next I'll go to next case, case 2. Special case. Case 2, when when the temperature at any point at do not change do not change with time means what? That is steady state. That is steady state means at a point the property called temperature is invariant with time. That is called a steady state. Steady state. Then dou T by dou T is equals to 0 means dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square plus Q dot by K is equals to 0. Q dot by K is equals to 0. This I can write it as del square T plus Q dot by K is equals to 0. This I can also call as Poisson equation. Okay, and this del square is nothing but Laplacian operator. Del square T is called as Laplacian operator of T. Laplacian operator of T. Laplacian of T or Laplacian operator T we can call this. Okay, now this del square T plus Q dot K is equal to 0. Suppose the case 3. For the case 2, no heat gain is also considered. No heat gain considered. Then this is equals to dou square T by, the equation is simplified, dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square is equals to 0, or del square T is equals to 0. And for a steady, suppose now I'll discuss one more condition for steady with no heat generation in case of one-dimensional flow. The equation is equals to be d square T by dx square is equals to 0. This is the various cases you come across in case of thermodynamics, and these cases are going to be considered. These equations are to be considered according to the situation you encountered. Okay, let's. This is about the in Cartesian coordinates the heat transfer coefficient, rate of heat transfer conducted in a three-dimensional systems. Okay, now we'll go to the next case, that is case 2, that is cylindrical coordinate system. Okay, cylindrical coordinate system, we will discuss about it now. Now already we defined what is isotropic material. Isotropic material is nothing but, for isotropic material the heat transfer conductivity, thermal conductivity Kx is equals to Ky is equals to Kz is K. Okay, means it is isotropic material. A material is called isotropic if the thermal conductivity in all the directions is same. Okay, I mean to say that. Okay, now this with this assumption, now I'll consider a cylindrical differential volume element which is of isotropic material, and its thicknesses are its thicknesses are dr or d theta and dz. I will try to draw that how it looks like the cylindrical coordinate. I will try to draw here. Okay, now for the sake of convenient, I will write here. I'll start here. This is y direction, this is x direction, and this is z direction. Just forgive me, I'll write it once again. This is z direction. Okay, now here I will take coordinates like this. This is this is, and here I will take this segment like this, okay, and I'll try to draw here. Which is of the form like this. I will explain to you clearly this about this one. Now I have taken here the angle is theta and this is d theta. Okay, and now as I said, its thickness are dr, d theta and dz. So here the thickness I have considered as this is equals to, I'll take from z direction. Right here, this is r d theta and this is dz and this one I am taken as dr. So thickness of small element which is in a cylindrical form dr in r direction or d theta in theta direction, and dz is going to be in z direction. Okay, respectively thickness are r r dr r d theta dz in r theta and z directions respectively. Z directions respectively. Okay, so according to first law, what it says, I'll write first law of thermodynamics like dq is equals to dE plus dW, or I can say delta U plus dW. Okay, and this is equals to this here. This factor is going to be 0 for solids, because there is no work done because of the temperature difference in case of a solids. Okay, now here therefore this dq is equals to delta U. That's what, where dq here, dq is nothing but heat gain due to heat transfer or exchange, heat exchange from the element, and then internal heat gain rate, heat gain or rate of heat gain due to heat transfer from the element plus internal heat gain. And delta E is equals to, again this is also, since you are talking about in heat transfer, therefore dq by dt is equals to delta U by delta T. So this is like this, I can say. Okay, delta U by delta dt. Okay, this is rate of change of internal energy. The cylindrical coordinates, I will try to do it so that you can able to understand what is exactly the picture and how the it I'll try to draw the diagram once again. This is the cylindrical coordinate I am trying to take. So, Okay, this is I'm trying to take. Okay. Now, so here this is the heat with which it is coming in. This is the radial direction as according to the through radius it is coming here like this along the radius, and it is going out at the rate like this. Heat is going out, heat transfer rate is going out at a QR plus DR. It's like this, and again now this is the next project. If I take this is Z, Z, this is QZ, and Q Z plus DZ. Okay, and next one is theta direction. Now this is theta direction. It just comes out like this. Q theta, and it is going out as Q theta plus D theta. Okay, like this. Now, for the sake of convenience, this is so I'll write it here. I'll show the directions also. This and this, okay, and this is X, Y, and Z, and this is D theta. This is theta. Okay, correct. So now this is dr. This I'll take here. This is dr. The thickness in r direction, and this is r d theta in theta direction, r d theta, and I will take this is dz, that direction. Okay. No. According to my earlier derivation, 1 plus 2 is equals to 3. One is net gain rate of heat conducted into the element dr or d theta dz. This is 1 plus heat generated rate in the element or d theta dr dz is equals to rate of change of internal energy of the element dr or d theta dz. Okay. This I'll put it in bracket. Okay. So now, first net gain rate of heat conducted into the element dr d theta dz is equals to, I can write it as, first I'll try to define qr is equal, this first one is equals to 100, first one is equals to, first one I can write it as heat conducted sorry, heat conducted into the element in r direction minus heat conducted out of the element in r direction. Okay, plus right, heat conducted into the element in theta direction minus heat conducted into the conducted out, sorry, this is heat conducted out of the element in theta direction plus heat conducted into the element in z direction minus heat conducted out of the element in z direction. So this is first. So first I will take the first section, heat conducted into the element in r direction. First, heat conducted into r direction denoted as QR is equals to minus K and area minus K A dot T by dou R. Therefore area normal to the direction of QR, the area normal to the direction of QR. So this is QR, and the area which is normal to the direction of QR is going to be R d theta. This is thickness, and this is the thickness which is normal. It means that R d theta into dz. Therefore R d theta into dz into dou T by dou R, and heat conducted out of the element in R direction is equals to denoted as Q R plus dr. Q R plus dr. This is equals to QR. Earlier also we have written in the same fashion, QR into dou by dou R, since I wanted to in x direction, into QR into dr. Right now, so for this, similarly, heat conducted. Okay, what I'll do, try to brief this equations. See, this I will call it as 1. This I will call it as 2. Okay, and this I will call it as 3. I call it as 4. I call it as 5. Call it as 6. Okay, now this is 1 and this is 2. Okay, now third one, heat conducted into the element in the direction of theta is equals to, this is equals to, I can write it as Q theta is equals to, since isotropic, therefore K into, now I'll go back to the sketch again. Here theta direction, this is direction of theta. In this direction it is coming, this is the element area normal to this one, the surface which is normal to this one is area which is normal to the Q theta is d, this is dr and this is dz. Therefore dr and dz. Okay, and dou T by here, the thickness, which is the thickness here, it is going to be not t, not theta. This is r d theta. The thickness is going to be, this is the thickness. Okay, so this is element cross section. This is a cross section and this is the length. It is therefore k by l. Therefore this is going to be dou t by dou x. Therefore this is going to be r d theta. Okay, this is very important to note down. This is important to note down. This is important to note down here. Okay, now similarly, this is third one. Okay, and fourth one would be, this is equals to q theta. Sorry, this is q theta. Okay, and the next one is equals to, in the heat conducted out of the element in the direction of theta plus in theta direction is equals to q theta plus d theta is equals to q theta plus dou r d theta dou by dou by r d theta. Is equals to q theta d theta into r. This is fourth. This is dou. This is dou r d theta. Okay. Right. Okay. Now let's go to that next fifth heat conducted into the element in z direction. Qz is equals to minus k into now here z direction. What is the z direction I have shown here? This z direction. So the area normal to this qz is going to be dr. This is dr and this is r d theta. Okay, that is equals to k into r d theta into dr dou t by dou z. This is fifth. Now go to sixth element. What is that? Is equals to q z plus dz is equals to qz plus dz is equals to, how we have written here qz plus dz, like q theta plus d theta. I will write it here the same way, is equals to qz plus whatever we have written dou by dou z of qz into dz. This is sixth equation. This is sixth equation form. Okay, now upon adding 1, 2, 3, 4, Sorry, sorry. Sorry, sorry. This is